Hello everyone, we the team Tigris of third year from EC department, Tyagaraja College of Engineering. In this video, we are going to explain the experimental study on short channel effect in double gate silicon carbide JFETs, and we are the team members. Introduction. Wide bandgap semiconductors have been used for power devices with low electric power loss due to their high breakdown of electric fields. Among wide bandgap semiconductors, silicon carbide is most hopeful one for fabricating ICs, and conventional CMOS circuits are not necessarily. With shrinking a channel length, on the other hand, short channel effects such as VTA shift, drain-induced barrier lowering, and subthreshold slope degradation occurs. In this study, the short channel effects in double gate silicon carbide JFET are experimentally investigated. A double gate JFETs. The double gate P and N JFETs were fabricated by ion implantation into 4 of HPSC and 4 HSIC substrate are grown by high temperature chemical vaporization method. The schematic diagram of fabricated n-FET is shown in the figure. The total ion implementation steps are 4. The value of L is in fabricated JFETs are of many ways, and 2.1 micrometer, which was confirmed by secondary electron microscopy observation. All the JFETs have been designed A of 1.5 micrometer, and the XY coordinate shown in figure 1 is used in the analytical solution of 2D Python 2D Poisson equation.
Hello everyone, this is Shaktivel. I'm here to explain the results and discussion of this research paper. Um, as you can see, this is the output or the drain characteristics of a n-channel JFET, and here is the output characteristics of a n-channel JFET, specifically the silicon carbide JFET, which is experimented, and this is the silicon carbide PJFET. Usually normal JFETs they would show a saturation, but here you can see that the saturation is not attained, which is mainly due to the short channel effects predominating, and this graph shows the transfer characteristics of uh, n-channel JFET, sorry, p-channel JFET, and this shows the transfer characteristics of n-channel JFET, and this is a silicon carbide p-FET and silicon carbide n-JFET. Now, from these graphs, we can infer certain results. Firstly, for a drain voltage of 0.05 volts, as the channel length becomes shorter, the magnitude of the threshold voltage increases. Like the shortest length, it has 16 volts of threshold voltage. Here too, you see the magnitude of the threshold voltage is like 16 volts for the shortest channel, and this is due to the this is one of the short channel effects. And other observation is that for two different drain voltages, if you plot the curve for the same JFET for the same length and same channel width A, you will see that the minus 2 volt drain voltage, it shows different threshold voltage. So this difference in threshold voltage, when drain voltage changes due to the DIBL, drain induced barrier lowering. So DIBL effect, due to that, you will see when drain voltage is varied, the threshold voltage varies for the same JFET. Now this DIBL, it can be measured using a factor called the DIBL factor, gamma S, which is given by change in the threshold voltage when the drain voltage is varied. Now, if you plot the gate voltage, that is, you see, the threshold voltage, it is fixed as the voltage at which the current is equal to 100 picoamperes. So your line is drawn over here. This line is 100 picoamperes. So at this point, the gate voltage is taken as the threshold voltage. Now, that with that being said, the gate voltage versus the drain voltage is plotted, and we get these kind of curves. We can clearly see that the for the shortest channel length, there is a least slope, and the inverse of the slope is the DIBL factor. So for the shortest channel, you see the DIBL factor is quite high. Similarly, the subthreshold slope. So before the threshold region, you can the curve shows a slope. This slope is called as the subthreshold slope. This subthreshold slope is ideally 60 millivolts per decade, but when the channel length is decreased, the subthreshold slope uh, shows a drastic increase, which is plotted in the table. Similarly, the DIBL factor also shows variations when the channel length is decreased. Now, this p-JFET has been modeled using 2D Poisson equations, which is shown here, and the experimental results have been compared with the analytical solutions. And turned out the curves, these points, they represent the experimental values, and they match very well with the analytical values obtained, the curves plotted. Thank you.
The S and SS values. SS also means that subthreshold slope obtained from 2 and 3 are plotted by the solid lines. Respectively, the experimental S and SS values also plotted where the values from a long channel 4.1 minus mu m double gate P and n-JFET are also added. The designed value is respectively is 1.5 mu m. The experimental A value is used as 0.9 mu m, which is discussed in the following. The theoretical value augmented the experimental S and SS values, which the clearly indicates that the analytical model is applicable to the double gate SiC JFET. L divided by A should be designed a larger than 3 times. This design a is not limited to SiC but also applicable to JFETs made by other semiconductor material. Not the temperature depends of SiC P and N JFET was also measured from RT to 573 Kelvin, which shows negligible temperature depends. A theoretical predicted by the author discussed the VTH values of SiC JFET fabricated in the study. VTH of the long channel double gate JFET assuming one-sided junction is given by the following equation. The equation shows that VTH equal to 5bi minus QND square divided by 8 epsilon s. To see the graph clearly explained to the equation, theoretical value and experimental value is equal to same as there in the graph, and dbil factor gamma is the A and the B graph is subthreshold slope SS. Square type is a JPJFET, and the triangle is a n-JFET, and the line is analytical model. is exponential increasing, and then experimental and theoretical values is extracted from also plotted, and then where and the equation is this, where Bi is built in the potential of the gate P-N junction, S is the permittivity, Nd is the net doping concentration, the channel region. In the JFET fully made by a ion implementation, also well known the JFET is an ion implementation, designed a value 1.5 μm in this study. The larger than the actual A value due to the lateral spread of the implanted ions. Some of the implanted dopants in the channel are compensated by the defect existing in the HPSI substrate. Considering them and V threshold obtained in the long channel JFET given in our previous study, the actual wave value is estimated to be smaller by 0.4 minus 0.8 μm than the designed value. The quantitative analysis, the lateral spread of the implanted ions, is our future study. The V threshold shift by the SCEs are not quantitatively analyzed in this study due to the difficulty of determining A and Nd in the channel, which are required from the obtaining the theoretical VTH. Thank you.